Thank you. So for the second lecture, I'm gonna start talking about deep inelastic scattering. So I'm done with the fundamentals of QCD, and you can talk about the QCDs for whole semester. There's so many fundamentals. Okay. Is it? Oh. It's working. So because quarks and gluons are confined inside of hadrons, we never really saw quarks and gluons in experiments. I mean, we never observed the directed fractional charge of quarks, right? We only saw the hadrons. So we want to understand the internal structure of proton or other hadrons, like how the quarks and gluons, they form these hadrons. So there's a few facts. First of all, proton is not just simply a static UUD bound state. It contains quarks and gluons, so it's better call it a many-body system of quarks and gluons. And of course, they are confined. So we have the valence quarks, like this cartoon shows. We have UUD in 3 colors. And then we also have C quarks pairs, which is from the fluctuation of a gluon into a quark-antiquark pair. And the different types of internal structure actually depends on different resolution scale we use to probe the proton. So for example, at very high energy or shorter distance, we might be able to resolve more partonic degrees of freedom. And so this is also an animation telling you that different values of X will have different structures inside the proton. Then take over to X.
There we go.
Oh, here.
That's not possible.
Can you full screen? Okay, this is, yeah, you can display it, it will repeat. So you start from the small values of X, which we'll talk about. And you go to some intermediate value of X, and then you go to large value. X is always less than 1, but the large value means it's the fraction of the 1. So you start from when the X value is large, it's similar to the valence picture of the proton. You have the 3 UUD quarks there. But if you go to the smaller value of X, you start with a completely different picture, like a cloud of gluons there. And then gradually you have the C quarks, quark pairs, and again, go to large values, you get the idea that depending on how you actually probe, how you actually see the internal structure, you will have different pictures of proton or in general hadrons. Yeah, I think I'm done. Wait.
Very good there.
Okay, so basically today, the second lecture, about the theory of deep inelastic scattering in the relatively large values of X, and the last lecture will be the physics when the X value is small. You can imagine that because you have different picture of what happened inside the proton, you probably have different physical descriptions in these 2 different regimes. Of course, that's not the only story we want to understand. There are many more fundamental questions people want to find answers. For example, how momentum is distributed among quarks and gluons, and how the mass and the spin of nucleons can emerge from quarks, gluons, and along with their dynamics. We have various hadrons, they have the mass, certain quantum numbers like charge, isospin, parity, and also strangeness, for example, and other quantum numbers. And we want to understand this so-called macroscopic property of hadrons in terms of the internal quark and gluon degrees of freedom. And you can also imagine that if it's a many-body system, there will be energy flow, and there was also pressures and shear forces inside the proton. And there's also the, in the small X regime, we'll talk about this so-called gluon saturation effect. Of course, most very important is how confinement, how quarks and gluons form these various hadrons in a dynamical process. So again, I'm only focusing, there are various ways of probing quarks and gluons inside hadrons. You can do high energy hadronic collisions or E plus, E minus scattering and other experiments, but I'm gonna focus on the deep inelastic scattering. In deep inelastic scattering, you have an energetic electron collide with a proton or other hadrons like deuteron, or maybe light nuclei, and also maybe heavy nuclei. Because the high virtuality of this virtual photon, which is characterized by Q square, you can see short distance. If you have large value of Q square, you have smaller value of Q square, you probably can probe the longer distance. So this is actually a slide generated by ChatGPT. Some of the figures probably are not exactly true, but actually there's a long history of using deep inelastic scattering to understand the internal structures of proton and hadron in general, and to confirm and test the QCD. Of course, we have the fixed target experiment at G-Lab, and then we also have the planned electron ion collider in the future. This one is under construction. To describe deep inelastic scattering, we need to introduce a few kinematic variables. Let's typically start to talk about deep inelastic scattering. There are a few quantities you'll use to describe the process. So the first one is, so we have an incoming quark with, incoming electron with momentum k mu, and the outgoing electron is momentum k prime mu, and the momentum transfer of this electron is q mu here. So the energy transfer is defined by this nu. From this definition, you can see that in the rest frame of nucleon or proton, that gives you the difference of the energy. That's why it's called energy transfer. And then there's we mentioned that the photon virtuality minus Q square. The photon virtuality is actually related to the, when you neglect the lepton masses, it's related to the mutual angle of the outgoing electron. And then we have the so-called Bjorken variable, xp here is the ratio Q square to P dot Q. By the way, P is the mass of the momentum of the proton. In the parton model, the Bjorken X is the momentum fraction carried by the partons or struck quarks inside of. We also have the so-called inelasticity is defined in this way. You see, we define everything in terms of the momentum of proton, electron, and virtual photon. That's basically how we introduced these various quantities. We also have the invariant mass of the hadronic final state. So we have the these virtual photons actually interact with the proton and generates whatever the final state. And it's characterized by this P plus Q there. That's the relative mass of final state. We also have the so-called central mass energy of lepton proton is given by the it's determined by the momentum of the electron and the proton. So generally, we talk about deep inelastic scattering. We want to have a large Q square, large resolution, and we also have the large central mass clear energy of the photon plus proton. So these 6 variables are typically people used to characterize the deep inelastic scattering process. So now we want to start to do the calculation of this process. So we have electron in, electron out, exchange the virtual photon with the proton, and then generate final state. So we write down this is the QED part because the interaction here is a QED vortex. It's electron, and photon. So we write down the using the Feynman rules. Just write down the vortex, outgoing, incoming, photon, propagator, and also we parameterize the electromagnetic interaction of the virtual photon with the proton. X is whatever the final state X. E is the incoming proton state. This is the electromagnetic current of the quarks inside of the proton. There are 6 flavors, so we possibly can add all the flavors. So the leptonic part is simple because it's QED. We can do calculation. But the hadronic part, the part that involves proton and the final state, are generally non-perturbative. We'll see how to deal with this quantity. So if this is the amplitude, you can square the amplitude, add the integration, final state integration measure, and divide it by the flux factor, you get the differential cross section. That's the then you group the terms into the leptonic part and hadronic part. Leptonic part is basically the square of this part. When you square, you get Q to the 4th. That's why you have the capital Q to the 4th. For the hadronic part, when you square this thing, you get 2 pieces. This is one, this is another one. And when you calculate cross section, you need to add the momentum conservation delta function, right? That's how you how to relate amplitude to the cross section. And then the momentum conservation delta function is absorbed in this hadronic tensor. That's you have 2 parts, leptonic part and hadronic part. The leptonic part is straightforward. If you have done any calculation in QED, this is pretty much, you convert this into the sum over the spins and it becomes the trace, and they use the identities of gamma matrices, and you end up with the leptonic part in terms of incoming and outgoing momentum of the electron, which is simple. For the hadronic part, we want to rewrite it in a more informative way or easier to deal with, because we don't know what this X is, can be anything. So the way we do this is we rewrite this delta function in terms of Fourier transformation, and then we use the translational invariance. So this we absorb the exponential so that we rewrite this J dagger mu at space-time 0 now becomes J dagger mu at Z here. That's how we use that factor. And once we use that factor to convert that into the spatial dependency, and there's no dependency on X in the here, and we can carry out the completeness relation. That's how we end up with the simpler form of this hadronic tensor. This 1/4 pi is more like a convention. Different people especially in the early literatures, they will use a different convention. And I also, so here I actually average over the final, over the proton spin sigma. Here I do not keep that because I'm dealing with unpolarized collision. So if you are dealing with polarized collision, you need to keep all these indices. So this is the hadronic tensor. So it carries two Lorentz indices. It depends on the momentum of P of the proton and the momentum Q of the virtual photon. You can form various of Lorentz structure, and then you impose the conservation of electromagnetic current, and in the end, you can find that it can be parameterized this way regarding its Lorentz structure. There's no physics here; it's just mathematics. You have two indices that what kinds of mu nu you can form, and then you just have this like a decomposition. But this W1 and W2 are known as structure functions. They contain all the non-perturbative information. If you use this form, W mu nu, when multiplied by this L mu nu, put into this form, and you get the final differential cross-section for the so-called inclusive DRS. Inclusive means I only measure the outgoing electron. I don't care what happened with the X part. This is the expression, so you can measure the outgoing electron and its angular distribution at the mutual angle theta. So they have different, at the mutual dependency, you can extract this W1, W2. So you can determine experimentally the structure function W1, W2. People like to use the dimensionless structure functions by redefine W1 and W2 in terms of F1, F2 here. So you only need this new variable. The new variable is what we introduced here. This can multiplied by this energy transfer. So if you look at experimental data, that's usually quoted using F1, F2, or other Fs instead of W. So we do have measurements, actually a lot, worldwide. We also have data from JLab contributing to F2 at the at tens of Q square here in this region. So this plot shows you the dependency of F2 with Q square. This should use the dependency of F2 with X. So it depends on the two variables. So of course, in the early days, there's this so-called Bjorken scaling that for moderate values of X, this F2 is independent of Q square. We'll see this later on. And another feature, if you look at the dependency on X, you observe that it's actually increasing rapidly when you are approaching the small X region for some not very small value of Q square. These quantities are indeed measurable from experiment. So how do we actually calculate this? So we have data and what QCD theory tells us about the F and F2. That's what we are gonna talk about in the rest of the lecture. Any questions so far? Yeah.
Sorry, you said that for inclusive processes, you mean you only measure the optical photon, don't worry.
I only measure the outgoing electron. So back to the picture. So I measure its outgoing momentum, and I do not measure what happened here. All right. So for the hadronic tensor, okay, this is in general, not in general, in principle, this is a non-perturbative object. We don't know how to calculate directly, so we don't know the wave function of proton. So what is the wave function of proton? And we don't, the low energy is probably in the non-perturbative region, and any perturbative calculations will be not good enough to make reasonable predictions. Also, the final state can be complicated. The upshot is this is a non-perturbative object. Very difficult to calculate. So instead, so this is also a diagrammatic representation of what this hadronic tensor is, or what we are dealing with, basically a virtual photon in and the proton also coming in, and then you have anything happening here, and then you square the amplitude. That's what the diagram shows you. So if you look at this expression, it's an integral. It's a space-time integration. It's actually more like a Fourier transformation because you have the phase there. So it's an integral over the whole space-time region. So instead of asking how to calculate the W mu nu, so the right question to ask, or what people pursued from this complicated object, is what space-time region Z is contributing to this integral. We are integrating everything, but not everything will contribute equally. Some regions of Z will be contributing dominantly. It certainly depends on what P and Q. There's some external momenta. So depending on what P and Q you put there, maybe you all need to consider different regions of Z. That's usually how people approach this. And P and Q, they form two Lorentz invariant variables. One is the Bjorken xb, x, and also another is q squared. So once you specify the values of x and q squared you are interested in, for example, if you look at the plots or data here, maybe I'm more interested in this region of x and q, or maybe I'm more interested in this region of x, q. Once you want to study what kinematic region, then a theoretical description will emerge. Hopefully it will emerge to help us describe that region. So there are two widely, this one maybe is more popular regarding the amount of activities in this region, the so-called Bjorken limit, which is when your Q squared, the resolution scale is very large. Typically when I say goes to infinity, it means it's very large. It will never go to infinity. And also the central mass clearing energy of the photon and proton is a similar order, so that their ratio B is fixed, it's finite, not very small, in the range of from 0 to 1. In this case, you might heard people talk about that this is a collinear region, meaning that your parton is, so if your proton is traveling very fast in this direction, so this collinear partons probably will follow a similar direction travel. Large component is following that. In this region, this is a dominant diagram. So here I just very schematically it's coming in, but in this region, I actually resolve that it's happening with the quarks there. This is the so-called handbag diagram, and eventually it will give us the collinear factorization. There's also the so-called Ray-J limit, which is the Bjorken x goes to 0 and your q squared is fixed. In this case, if you look at the definition of Bjorken, it means your central mass energy of photon and proton is much larger than your resolution scale. So this is the largest scale in the process. In this case, the dipole picture actually is the dominant contribution. So you have a virtual photon in with your proton. If you try to see what happens, this is what happened. You have a photon fluctuating to quark-antiquark pair, and they scatter through the proton. That's what is in the rigid limit. So first, or in today's lecture, I'm first talk about this. The last lecture will about this. So in the Bjorken limit, how do we deal with the, I said, once we specify the kinematic rate and we want to study, maybe there's some simple description of the hadronic tensor will emerge that help us describe physics in that region. So what happens in the Bjorken limit? Let's see. So how do we do the calculation? So we start from the definition here. We know that this electromagnetic current in this form, you have all the flavors. Each flavor carries different electric charge. We just put in the expression here. We have two currents, we put it there. Next step, at the lowest order, we decide to contract these quark fields to generate a propagator. So it's essentially calculating this diagram. So I have one quark propagator here. I also have another propagating here, but this is crossing the cut line here. So I need to put this. This is like a final state quark. It is on mass shell. So so I basically contract these two. That gives me, I didn't write this down explicitly. So I contract these two, that gives me the propagator, and then contract these two to get. So I have two propagators. Okay, I skipped many details here. So then you substitute the expression of the propagator. One propagator is a cut propagator, meaning that I'm not sure. So this contain, okay. So this is this propagator here. So it's on mass shell. And you have another one that's not on mass shell. And then remember, we also, okay, sorry, I said something wrong. So we only have one. It's only one. We only contract one here. We only contract this propagator. This field is from the proton. That will be part of the quark distribution inside the proton. I will need to use that to define. So you see, I have this one. I'm not dealing with it. I just left its quark field. It's used to calculate the matrix element between the proton state. Eventually, this gives me the quark distribution inside the proton. But I need to contract one propagator here and put it on mass shell. And that's how I get the result here. So I haven't, okay, I'm actually using the Bjorken limit. There's a series proof in the first reference I listed why this is a dominant diagram. It needs proof. I cannot just tell you without proof. Yeah.
For the quark correlation function is indices like I and J. I'm guessing for the initial and like final state.
Filter bit.
For the quark correlation function, there's indices like I and then J on the on like psi and psi bar, and then also in the function itself.
You mean
That
this index?
Yeah, what exactly are those indices referring to?
Oh, this I and the J, they are. So we are taking a trace here. So these are the Dirac-Spinner indices.
Okay.
Sorry, this is not current indices. We introduced the electron. This is because up to now there's only electromagnetic interaction, and IJ is, so these are spinors, right?
Okay.
We have so that means you have this I, gamma mu, IJ, Zj. Because this is the 4x4 matrix, this is the 4D, this is row, this is the column.
Right.
And then then we take the trace. So we have the trace, we have the gamma mu there. These are the spinners in Dirac spinner space. Yeah.
Yeah. And so when you take that trace, are you taking it over the spinner space or are you taking it over the flavor space? The trace and the.
It's a sum. Trace is over the in the spinner space.
Okay, gotcha. Thank you.
Okay. So we have this form. This part phi is dependent on the proton wave function, and you have this H, which is just some matrix element in spinner space. Okay,
Also another.
So is this correlation function being defined here, or is this coming from somewhere else?
this one.
Yes. Is
This
this
one is
defined by like this group of terms in the hadronic tensor, or does
Yeah,
it?
because so you see, I have a four field, 1, 2, 3, 4 here. I contract these two. These two are left. That two left is here. They become that will be representing how you pull out a quark from your proton. Okay. Well, how many of you are? Yeah.
What do you mean by leading order? And why could you track different quarks? Because we are not in free fields here. This is not Gaussian free field.
So this is a diagram we want to calculate. This part is free. This is the outgoing quark. I can do contraction. But this part is from the proton. I didn't do anything. I just leave it there. That's the field.
So this is mainly the previous diagram.
Yes, that's basically calculating this diagram. As I said, in the Bjorken limit, people made their career to prove that this is the leading diagram in the Bjorken limit. In the Bjorken limit, you should focus on that. That is correct. Okay, how many of you are familiar with light cone notations? Okay, very few. So I probably will not go that in detail, but we'll use this. So typically you have a P in momentum, you have in Cartesian coordinate, you have the time and the three spatial component, but in light cone coordinates, so we reorganize. We have this plus, which is given by the time component and the z direction. It's a linear combination of your time component with your z component with your momentum. And then sometimes you just write this as P plus, P minus, and P perf. So the reason we are doing this is there is a preferred direction in Clarion. So you have two beams. So most of your beams are along the z direction. So your momentum along the direction is usually very large, but its transverse momentum is usually very small. And if this is on mass shell, it means your P0 square is P1 plus P2 square plus P3 square. If this one is very large, this is very small, it means your P0 is basically determined by P3. If you form this one is very close to 0, this one is very large. So this usually is very convenient. We will talk about quark is collinear to a proton. It's basically saying that is this momentum is similar, it's in the same direction. So it's just, basically I'm gonna use analytical coordinates. Okay, maybe I should just explain the idea instead of going through the derivations. So you look at this expression, so it's a convolution, or the two factors are convoluted by k. That's the integration momentum, right? In principle, you need to integrate over all the possible momentum k there. But in the Bjorken limit, people showed that, oh, you only need to, the dominant contribution, as I said, oh, when you do an integration, what is the integral? You integrate everything, but not everything contributes equally. You want to figure out what's the most important contribution in this integral. People prove that in the collinear, the Bjorken limit, most important contribution of k is the collinear part. So you have k, basically it's just, so p is the momentum of proton. How many?
The black one. Black marker.
So this is k. So your momentum can be different values, is component, but this is called factorization theorem, collinear factorization theorem, saying that, oh, dominant contribution is you only consider momentum that is in this form. That it's only the collinear part that dominates. The other parts, maybe they are there, but they are so small compared to this component, you can essentially set them to zero. At least that's the leading contribution. If they have a small values, you can always take in the corrections. But if you want to talk about the leading order contribution, that's basically what happened there. So if you set this integral to be just the collinear momentum, which is also characterized here, you can make many simplifications. Eventually, okay, I should also, you have a four momentum. You have h, mu nu, and you have phi, both dependent on k. But so so basically the collinear limit, your hard factor will be only sensitive to the collinear component of your momentum. So this is the dx part. And your dk minus and dk part will be only in this k. So because your hard factor, sorry, this is not p, this should be q. Q is very large. It's on the order of capital Q. So in this collinear limits, this convolution factorized into a very simple form. Your plus component is basically only with the hadronic hard scattering part, and your k minus and dk part is related to the non-productive object. That's what happened if you accept that the only dominant contribution is when this is collinear and it is sensitive to the hadronic hard scattering part. These are all these algebras will eventually tell you in the end you have this factorized form of the hadronic tensor. So this QC is essentially the X I'm using here. So now you only have the convolution of QC here, because the other part is absorbed into the matrix element. That's how you actually the dk minus and k perp part, and the k perp part you can actually carry out the integral. Essentially, it's a transverse coordinate delta function. So the two transverse coordinates are the same. The only thing that's left is the, I think there's a definition here. Yeah, there's definition. The only thing that's left is along the z minus direction coordinates. That's essentially the Borman's demonstration factorization. It's not a full order proof, but it shows you that what happens when you take the collinear approximation. So in this regime, we actually express the hadronic tensor in terms of hard scattering factor, which we can actually calculate, because it does not depend on the proton wave function. And then we also have the Parker PDF, which is a non-perturbable object that depends on the proton wave function, which we don't know how to calculate. But this is very encouraging because I think the important message, which I'm not proving anything, I'm just stating that this PDF is actually universal. It's not just in this one process. If you can determine this PDF in the DIS process, it can be used in the hadronic Layton process. So it's actually very, the predictive power is far beyond the deep inelastic scattering. And that's also that's the power of the collinear factorization. At least for this leading order in the hard scattering process, we have this factorized form. This is for W mu nu. We can actually project out F1 and F2. Remember, we express the W mu nu in terms of W1 and W2. W1 and W2 are related to F1 and F2, so we can actually project out the structure function F1, F2 from the expression of W mu nu. Using this can be carried out. So this will be some very simple. Notice that at the leading order, this C is actually the Bjorken XB here. So you can carry out this integration. That's what we end up with the expression for F1 and F2. From this expression, you can directly see the relation between the F1 and F2. This relation is also called Klein-Gross relation. Another important property of this calculation is the structural function is independent of Q squared. So you, at least at this leading order, you only have dependency on X Bjorken. You don't have the dependency on Q squared. That's pretty much what was observed in the early days of deep inelastic scattering. You have or not very small or not very large X. You do have independency of Q squared over a wide range of scale here. So that's the so-called Bjorken scaling. But of course, if you go to smaller value of X and or closer to 1, your scaling is the Bjorken scaling is violated, meaning that your leading order calculation here is not sufficient. You need to take into account the QCD interactions. So in this calculation, the interaction is only electromagnetic. This part is part of the PDF. All the interaction is here. To understand the data, we need to take into the interaction of QCD, which we'll talk about in the next lecture. I think the end of my
And for the questions?
So I might be messing up big time because I'm not a theorist, but for instance, what's the difference between this type of factorization and the factorization that you do with OPE?
I do with what?
With OPE, the operator product expansion, what's kind of the difference? Do you get to the same result or?
I think there's a more formal way of doing this collinear factorization. OP. We correctly, because experts on this collinear factorization, OP is a formulation of collinear factorization.
It is a formulation. It's valid only for inclusive scattering. The collinear factorization is more generalizable, and as you will hear a lot in the school, the strict connection is between x-weighted moments of the structure functions and what you can calculate with OPE. So OPE calculates or can talks about factors, talks about the moments, x-weighted moments of the structural functions. So that's a connection. In that sense, they are equivalent. But then collinear factorization can be extended to many more processes.
Thank you.
More questions?
Could you think you could say a little bit about why like the handbag diagrams are more prominent in the Bjorken limit, whereas the other diagrams are more prominent in the regular limit? Like, what's the difference between diagrams that makes them more prominent in those different regions?
One.
Is there like an intuitive?
Oh, okay. I think so so if you think of this I think if you think of this as a propagator, so the major contribution is from when this quark is almost on shell. So it's chi-square close to 0. I think that's I'm not sure, Alberto, you want to add why this is the dominant diagram? It's a simple explanation rather than the general proof why this is related to pinch singularity. That's moving towards the proof. No very simple explanation like, oh, why this is the dominant.
Well, there are a couple of things. From a power counting level, you have only one we are no powers of alpha S, so you don't expect other vertices going around. Then you might ask several other things. Why don't you have exchanges in which a quark goes back to the blob? And that is because every time you get something else interacting with the blob, with the remnant of the proton, you get a suppression of 1/q to the cross section. So that makes those diagrams subdominant. And you have only one quark going out, and the cut there indicates that the quark is on shell, at least theoretically, because there is no on-shell quark, there are no free quarks. So that is valid in the limit where X is not too large, and therefore there is enough energy for the quark to fragment, hadronize in many states. And then you can apply the completeness in Fock space of the hadronic states, and you can remove all these final state processes. So effectively only a flying quark remains. Things change when you get close to X = 1 because you don't have enough energy left for the quark to do much. And then you need to consider more complex diagrams. Yeah. So if you are in for a lot of technical discussion, the book by Collins does pretty good job. But it is a hard read. So yeah, approach it with caution.
It goes through the intro of MS pattern model. This diagram or the prediction of the because this is the electromagnetic interaction, it will only interact through electric charge, and inside the proton, only quarks carry electric charge. And because you have a very high resolution scale there, so it's like a point-like interaction with point-like particle there. So it will only interact with one quark there inside the proton by kicking out that quark outside this very naive pattern model. There's also a time scale of the interaction of the photon with your partners. The scale is so short that other interactions within your proton will not influence your single interaction of your photon with your. These assumptions under this limit, that's what happened with pattern model. At least this is like a more pure theoretical way of formulating the pattern model.
Yeah, thanks for the talk. So I want to ask, like, when people try to identify the important region for that, let's say the integral in the hadronic tensor, typically what people do is argue the most important contribution from the integrand. Like you start with a homogeneous proton, and you do a boost, and you identify the most important contribution. But why people, because you are dealing with the whole integral, what about the measure? The measure part, you only consider the integrand, but how about the measure? Such as this very simple measure, like just the delta function measure here. What if we have a more sophisticated situation, like you know, like a jet, or like you have a theta function measure without just a single delta function measure here? Yeah, if that makes sense.
That sounds a more difficult problem beyond the inclusive DIS I'm talking about. In my discussion, there's no jets. Oh, I would say it's inclusive if I actually don't need to look down the final state.
I see. So maybe I can just make this question simple here, like, when we try to identify the PDF definition, which is just along the collinear direction, the most important contribution, you're just identifying the integrand. How about there's a e to the IQZ factor? Like is a whole integral that apart from that integrand, you have a mirror.
Oh, I think in the case of in the Bjorken limit, what people said is I only need to consider z, which is the this z is the distance between 0 and z, which is the distance of two space-time points. And what people said is I should only consider the light separation. That's the dominant. It's not any z, but it's like z square close to 0. That's the major.
Yeah,
contribution.
like when people do this argument, I think it's just you arguing from that particular operator's definition, like the P, that sandwich, but without considering that extra factor.
That is purely kinematic. You have Q, which is very large. You can just what parameterization of that Q, but this when the alternative is very large, you can show that this Q dot Z, this part, because you don't want some large values here because it will be highly oscillating phase, meaning that anything that is weighted by that highly oscillating phase will be not contributing. When Q square is very large, it is by the value of Z square is like it is like separate. That's a so-called Lycon expansion. So you have the dominate one, and then you expand that. This analysis is standard kinematic. It's not related to any. It's based on the simple idea that I have a potential phase. I know certain information about this Q, which is some external input, meaning that I cannot have a very large phase there, major control. Then I determine which region of Z is contributing.
Thank you, thank you.
More questions?
I wonder, is it possible to calculate the subdominant contribution of this Q square goes to infinity?
Okay, so this expansion is only valid at the leading order of expansion of 1 over Q square.
Yeah, I mean, could we calculate could we calculate that order lambda's QCD square over Q square?
Yeah, there are, I think next to leading order, next to leading power probably have already been done many, many years ago. Elastic, inclusive DRS. I think even I didn't follow recent research, but I believe they are probably calculated to even higher order.
Oh, okay, thank you. My next question is, we know that there's a Wilson line between in PDF between the two quark fields.
Yeah, or the next lecture. Of course, this is not gauge invariant.
Yeah, I mean, we know the diagram should be gauge invariant. So where did you break the gauge invariance in the whole derivation?
Because when you include a gluon, for example, you have a higher order in alpha S.
I'd like to order.
So this calculation is. Sorry?
A couple check interrupts.
Ryan, can you please close the microphone?
So this calculation is the lowest order in alpha S. If you want to add a Wilson line, you basically put many gluons, collinear gluon extend here, each collinear gluon will introduce alpha S. So you basically are doing high order perturbative effect. And I'm not sure, what's the question?
So this simple diagram isn't gauge invariant. You mean this?
It is in an axial gauge. So the dominant part, along with this diagram, in the dominant contribution, there are a lot of A minus exchanged gluons, only the minus component of the exchange gluons. And then you can choose the gauge in which A minus is equal to 0. So you fix the gauge to make all what you don't see disappear. That is a choice of gauge. If you change gauge, you will see a Wilson line appearing in between the two Cork fields. So that's how you get gauge invariance. But in a simple discussion, you assume the axial gauge A minus equal to 0. And in this diagram, all of them disappear and only the two Cork fields remain.
Okay, thank you.
That's one reason why it's good to choose axial gauges. There was a question earlier. But it's difficult to make it's more difficult to make a calculation, and gauge invariance is not obvious.
So it seems there are no questions.